So in section 11-3, we're going to be talking about infinite geometric series, and we're going to start off with this sum. And what you'll notice is it's geometric because I'm multiplying by 1/2 to get from one term to the next. So I keep multiplying by 1/2 to get to the next term, and so on. So the other thing that makes this infinite is the dot, dot, dot. I'm not going to add like 10 terms or 12 terms. I'm going to add an infinite amount of terms. And I want to see what the sum is approaching. So what I'm going to do is use the calculator to help me out. So what I've done is I've found the sum of the first 10 terms right here. And then, so if I were to continue this out for 10 terms, the sum would be 0.999023. And then what I've done next is I found the sum of the first 30 terms. So continuing this out for 30 terms, adding them all together, what I end up getting is 0.999999068. So it's getting really, really close to what it's looking like when I go ahead and sum up the first 100 terms. I end up getting the calculator's answer as 1. So what's happening is that this sum is approaching 1, and it's not going to go over 1 because notice what's happening with the numbers. The next one will be 1 over 64, and the fractions are getting super, super small, so what's ended up happening is I'm not really adding much to my decimal. So I end up eventually just adding nothing or something so small it doesn't have a significant effect on the sum. So the sum, it looks like it's approaching as 1. So what we're going to be doing is coming up with formulas to find the sum of an infinite geometric series. And it all depends on the common ratio, R. We don't want to have to add up, 100 or 1,000 to kind of figure out what the terms are approaching. So there's got to be a formula to just tell us what the sum is approaching, and here's what it is. So case 1 is if the absolute value of your common ratio, so remember this is the common ratio, if the absolute value of it is less than 1, then here's how you find the sum. You take your first term, so this is your first term, and your common ratio, and you do the first term over 1 minus your common ratio. That tells you what the sum is. So let's go back to that example that I gave a few minutes ago, the 1/2 plus the 1/4 plus the 1/8, where I ended up finding the sum of the first 30, then the first 10, 30, and 100 terms, and I found out that the sum was approaching 1. Well, now if I look at the common ratio is 1/2 because that's what I'm doing to get from one term to the next as I'm multiplying by 1/2. And so since the absolute value of 1/2 is less than 1, so I'm using this right here, I know that I'm going to use this formula. So the sum would equal the first term, which is 1/2, over 1 minus the common ratio, which is 1/2. Well, basically I get 1/2 over 1/2, or 1, and that's what I got on the calculator by just summing up a whole bunch of terms. So that brings us to case 2. What if your common ratio is bigger than or equal to 1? Then your sum is either going to be infinity or negative infinity, and it all depends on your first term. It's infinity if your first term is positive, and it's negative infinity if your first term is negative. So here's an infinite geometric series, infinite from the dot, 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 geometric because I'm multiplying by 3, and I had put an 8 in there. It wasn't supposed to be there, so when I multiply 6 by 3, I get 18, and then 18 by 3, I get 54. So this is geometric where R is equal to 3. So notice that this is bigger than or equal to 1. So I know my answer, these are going to be infinity or negative infinity. Well, if you just kind of look at this sequence, if I add 2 plus 6 plus 18 plus 54, the numbers are getting they're getting larger, so the sum is going to get larger. And since the first term is positive, that means the sum is going to be infinite. If I were to keep adding more and more terms, the sum would just get bigger. Alright, and here's the last case. So you have an infinite geometric series, and what if your common ratio is less than or equal to negative 1? What ends up happening is no sum exists. So here's an example. So I have sequence 3, then negative 6. So it looks like I'm multiplying by a negative 2 to get from one term to the next. So I'm multiplying by negative 2. So negative 2, so since r is equal to negative 2, negative 2 is less than or equal to negative 1. It's smaller. So what happens, what this means, is no sum exists. And I'm going to show you why. So I'm going to start by adding the first two, the 3 minus the 6, so these two. If I were to add those together, I would end up getting negative 3. So then I'm going to go ahead and add the next term, 12. So when I add the next term, I end up getting 9. So then I'm going to add the next term, which is negative 24. So then my sum ends up being negative 15. Then I'm going to add the next term, and I'm going to add 48. So my new sum is going to now be positive 33. What ends up happening is my first sum was negative 3, then my second sum was 9, and then my next sum was negative 15. What's happening is I'm not approaching a single number. I'm going from negative to positive to negative to positive. It's not approaching one number. So what happens is that the sum does not exist. So I'm going to show you what ends up happening by adding the first two terms together. If I do 3 minus 6, I end up getting negative 3. And then I'm going to add the next term, which is 12. When I add the next term, I end up getting negative 9. Going to the next term, which is positive 9. I'm going to add negative 24. And I end up getting negative 15. Then I add the next term, which is 48. I end up getting a sum of 33. Let me backtrack and show you what happened. The first sum was negative 3. Then when I added the next term, I got positive 9. Added the next term, it went negative again. Added the next term, it went positive. What's happening is these sums are going from negative to positive, so it's never approaching a single value, so the sum does not exist. So now here's a series, and you're asked to find the sum. And so what you're going to have to do is find the common ratio. So what are you doing to get from one term to the next? And it looks like we're multiplying by a negative 0.2. So if I multiply this by a negative 0.2, I end up getting positive 0.04, and so on. So r is equal to negative 0.2. So what that means is we're going to try case 1. Is the absolute value of negative 0.2 less than 1? If it is, we're going to use this sum formula, first term over 1 minus r. Well, the absolute value of negative 0.2 is just 0.2, and that's less than 1. So yes, we're going to use this right here. So we're going to take our first term, which is 1, and then we're going to do 1 minus the common ratio, and the common ratio is a negative 0.2. So I end up getting 1 over, and this ends up being plus a 1.2. So when I simplify that, I end up getting 0.83 repeating, and that would be what my sum would be approaching. So I had to find the common ratio first, and then I had to plug it in to see if I could use this formula right here by seeing if the absolute value of that was less than 1. If it is not, I can't use that formula. So for this one, to get from one term to the next, it looks like I'm multiplying by 1.1, because negative 1 times 1.1 is negative 1.1. When I multiply 1.1 by negative 1.1, I end up getting negative 1.21. So it looks like the common ratio is 1.1. So is the absolute value of 1.1 less than 1? If so, I'm going to use the formula that I used before, a1 over 1 minus r. Well, this is not true, so I'm not going to use that formula. So I go to the second case, case 2. Is r bigger than or equal to 1? Absolutely. So when this was the case, then that means the sum is either infinity or the sum is negative infinity. You have to pick. Well, look at the terms. When I add them together, they're becoming more and more negative. So that means the sum is negative infinity.